Boron is one of the more intriguing elements in the periodic table, often overlooked but essential in both nature and industry. With the atomic number 5, boron sits at the border between metals and nonmetals, making it a metalloid. This intermediate position is more than just symbolic. It gives boron a unique set of properties that allow it to behave in ways that are both metallic and non-metallic, depending on the context. Chemically, boron is quite versatile. It typically forms covalent bonds and is commonly found in nature in compounds such as borates and boric acid, rather than in its elemental form. Elemental boron is rarely found naturally because it's highly reactive in its pure state. Most naturally occurring boron is part of compounds like borax, kernite, and colomanite, typically sourced from places like Turkey, the United States, and Argentina. In its crystalline form, boron is extremely hard, comparable in some cases to diamond. It has a very high melting point of around 2075 degrees Celsius, making it useful in materials that need to withstand high temperatures. Its amorphous form, by contrast, is a brown powder with lower hardness and reactivity. This duality again reflects boron's transitional nature as a metalloid. One of the most interesting aspects of boron is its electron-deficient bonding. It forms clusters and complex molecules, like boranes, which don't follow the typical rules of chemical bonding. These structures have inspired significant research in theoretical and applied chemistry, and boron chemistry has played a central role in advancing our understanding of molecular bonding. Biologically, boron plays a role in the metabolism of plants. Although not needed in large quantities, it is essential for cell wall formation and the development of reproductive tissues in many plant species. Boron deficiencies in soil can lead to stunted plant growth, deformities, or even crop failure. In animals and humans, the role of boron is still being studied, but there is evidence suggesting it contributes to bone health, brain function, and inflammation regulation. Small amounts of boron in the diet appear to be beneficial, though excessive intake can be toxic. It's a perfect example of the fine balance often required in trace element nutrition. From an industrial perspective, boron is incredibly valuable. It's used in a wide range of applications, from glass and ceramics to semiconductors and aerospace materials. One of its most well-known applications is in borosilicate glass, which is more resistant to thermal shock than regular glass. This type of glass is used in laboratory equipment, cookware like Pyrex, and even in certain types of smartphone screens. Boron is also a critical component in fiberglass production, which is used for insulation, automotive parts, and construction materials. In metallurgy, small amounts of boron can significantly improve the hardness and strength of steel alloys. Boron steel is used in automotive safety components, such as door beams and structural reinforcements, due to its high tensile strength and low weight. Another fascinating application is in the field of nuclear energy. Boron-10, a stable isotope of boron, has a high neutron cross-section, which means it's excellent at absorbing neutrons. This makes it a key material in control rods in nuclear reactors, where it helps regulate the fission process. It's also used in radiation shields and detectors. Boron's neutron-absorbing abilities have also led to its use in medical treatments, such as boron neutron capture therapy, BNCT, an experimental cancer treatment that aims to selectively destroy tumor cells while minimizing damage to surrounding healthy tissue. In the world of high-tech electronics and nanotechnology, boron is making its mark as well. Boron nitride, for instance, is a compound with properties similar to carbon-based graphene. Hexagonal boron nitride is used as a lubricant and as a thermal conductor in electronic devices, while its cubic form is nearly as hard as diamond, making it useful in cutting tools and abrasives. More recently, researchers have been exploring boraphene, a two-dimensional form of boron that could rival or even surpass graphene in certain electronic and mechanical properties. The history of boron's discovery is also worth noting. Though boron compounds have been used for thousands of years, ancient Egyptians used borax in mummification. The element itself wasn't isolated until the early 19th century. In 1808, both Sir Humphrey Davy in England and the French chemists Joseph-Louis Gay-Lussac and Louis-Jacques Thénard independently succeeded in isolating boron using chemical reactions involving boric acid. However, the pure element wasn't fully characterized until much later due to the difficulty of producing uncontaminated samples. Economically, boron is a strategically important material. Turkey holds the majority of the world's boron reserves and is a leading exporter. The United States, Russia, and South America also contribute significantly to global production. Because of its wide range of applications in everything from agriculture to defense, maintaining a stable supply of boron is considered important for national security in some countries. Despite its widespread use and importance, boron remains relatively obscure in the public consciousness, perhaps because it rarely appears in its elemental form and isn't commonly discussed outside of specific industries. But its influence is everywhere, from the glass in your kitchen and the fertilizer in your garden to the shielding around a nuclear reactor. In a way, boron is a quiet enabler, a background element that plays critical roles in systems that we rely on every day. What makes boron particularly exciting is the future potential it holds. As technology continues to advance, the demand for lightweight, high-strength materials is increasing. Boron-based compounds fit this niche perfectly. In energy storage, boron is being studied for use in advanced batteries and hydrogen storage systems. In pharmaceuticals, boron-containing molecules are being investigated for their potential in treating cancers, fungal infections, and other diseases. The field of boron chemistry continues to be a rich area for innovation and discovery. In summary, boron is far more than a simple element on the periodic table. Its unique position as a metalloid gives it properties that are both challenging and incredibly useful. From essential roles in plant biology to its critical applications in nuclear power, glass manufacturing, and future technologies, boron quietly supports a wide range of industries and scientific advancements. Whether in the soil beneath our feet or in the most advanced electronics, boron exemplifies the complexity and interconnectedness of the material world.